The presentation. Okay, so good evening, Professor over there and everyone. My name is Hoang. Today I will be presenting my evaluation of model performance on a student academic data set which I have generated before self-generated. And specifically, this set will focus on the applications and performance of supercomputer machines, AVM. To begin with, what is an SVM? It is a supervised machine learning algorithm that can be used for both classification and regression tasks. The primary goal of unsupported machines, SVM, is to find optimal hyperplane or decision boundary that best separate data point into different classes. Its core principle is to find the boundary that maximize the margin between the classes. So FVM supported with the machines have several key advantages. They are highly effective in high-dimensional space, which is useful in case where the number of dimensions is greater than the number of samples. When when the number of features is greater than the number of records, yeah, they are also memory efficiencies because the model is built using only a subset of training point. Because of this strength, supported machine are widely used in applications like image recognitions, text categorizations, and bioinformatics. So we talk about the core principle of supported machine. This slide illustrates the core principle of an SVM supported machine. The hyperplane, this is the decision boundary itself, which separates the data into classes. Yeah, you can see that. The margin, this is the distance between the hyperplane and the closest data point from each respective class. So the support vector, there are most crucial data point in the dataset. They are the point that closest closest um, to or on the margins, and they are the only point that define the hyperplane position. So the main objective of the algorithm is to find the hyperplane with the largest possible margins, which have the model generalize better to new or unseen data. Now, but what if the data is isn't a simple, right? Like a straight line? This is a common challenge known as nonlinear classifications when the data can't be separated by a single plane in its original state. We so we have to use the kernels. So they are the kernel chip that we have learned or have heard from previous lectures is a powerful technique that maps the data into a hyperdimensional space like this from 3D to from 3D, 2D to 3D dimensionals. In this new space, the data can separate by a linear hyperplane. Hyperplane. This is done efficiently using an implicit transformations, which avoid the heavy computational cost of explicitly transforming the data. So as seen in the chart, common kernel type include the linear kernel from single data as well as the RBF and polynomial kernel, which are versatile and can handle complex nonlinear parallel. The best kernel to use is highly dependent on the structure of the dataset itself. So let's talk some statistical background to from the previous lectures around uh, to the 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 weak second lectures. So to properly build and evaluate our model, we rely on several foundation statistical concepts. This includes understanding our features as random variable. We can be discrete and sorry, we can be discrete or continuous and described by probability function. Expected variations, expected and expectation and variance. To understand the average value or the mean and the spread of our data, right skewed or left skewed due to right tail or left hand tail. Yeah, finally, the conditional probability and bias rule are essential. Bias rule provide method to update our belief based on new evidence, which is fundamental to modeling, inference, and evaluation. Yeah, marginalization for evaluation. Law of total P, finding marginal probability using conditional probability. Yeah, so the purpose is essential for inference and evaluation in a complex model. Now I talk about the project. So for this project, I used a generated data set to model student academic performance. This is a large scale data set. I have again a set generated with 100 and 110,000 records. In what the document include task one, generate the data sets, and task two, how I apply as some of the machine on this uh, on my data sets that I have submitted before from in a PDF file include two of those tasks. So in here, I will briefly talk about my data sets. The data generation to ensure the data was realistic. Features were created with a specific distribution. For example, study hours, which follow a gamma distribution to ensure that the right skill and family income follow a log normal distribution. And the key features, the key column here, the features area for prediction include study hours, sleep hours, stress level 1 to 10, previous GPA, and family income. I have clearly explained how I generated that column in the PDF file that I was submitted before. You can take a look at this. Um, Take a look at this to understand more of my data set. I have created it with NP random. With the random seed is my student ID. So about the band the target features, the binary the target features. The variable, the target variable performance or not performance, and what has encoded to 1 and 0, which was specified as high and low, and based on 60 percentile threshold. We Here is the distributions of the data sets from different features. In this slide, it's quite small. You can watch it clearly in my PDF file that was submitted from LMS. So the objective is the overall is to evaluate the supervised machine ability to accurately predict a student academic performance beyond these features. And about the supervised machine, I have used the provided code from professors and fit it with my datasets to watch how supervised machines actually do in doing in my datasets. I have submitted with the PDF file. Right. So in this slide, I will talk about the resolve the confusion matrix of the model performance. So this bar chart visualize the confusion matrix, which give us a detailed breakdown of the prediction result. With true negative, 12,852 students with low performance were correctly predicted as low, and true positive, 7,618 students with high performance were correctly predicted as high. From those confusion matrix value, we can calculate our overall performance matrix. The SVM model achieved an accuracy of 85.3%, yeah, round it to 1 decimal. And furthermore, the weighted precision, weighted recall, weighted F1 score were all consistent at 0.85. It's quite small to look clearly in the slide. You can watch it in the PDF file I have submitted in LMS. Here is the visualizations about the 2D decision boundary. This graph provides a 2D visualization of the model decision boundaries. It's plot study hours against sleep hour to create this 2D view. The track level features were held constant at a fixed average value of 5.1. The boundary line separating the red and blue regions show where the model switch its prediction from low to high performance based on just these two features. And to figure out more, this visualization is better in 3D design regions. So to get a more complete picture, this slide shows a 3D visualization of the S of the supervised machine design region. This plot includes study hour, sleep hour, and stress level. The contour slide shows how the design surface that separate the two classic blue and red dot. It's not a simple flat plane, but a complex nonlinear surface that bend and shift depending on the stress level of the student. So in this, we can see clearly that student with less study hour will be labeled as low performance, right? And the more they study, the more the more the more proportion they be labeled. They will be labeled as a high performance. Here the final slide showing terminal output. We confirm our finding. We can see the detailed classification report the final accuracy score of approximately 85.3%. Yeah, you can see it. And just below it, we also see the neural nested accuracy of 0.80 8534. Yeah. To confirm my early point that superbetter machine was just slightly below the neural network. But in conclusion, the superbetter machine model proved to be highly effective and robust as classified for this start for this for this my test generator. It achieved 85.2% accuracy on large and complex data. Um, Not complex because I just created 5 features to figure out, understand more of the superbetter machine. Thank you for listening. I'm ready for any question. Feel free to ask for um, ambiguous or anything. Uh, Thank you for listening. Stop. Goodbye. Stop recording.